Hey guys, welcome to another lecture. In this one, we're going to be talking about electromagnetic waves. Um, so how we're going to start our discussion is kind of going over some stuff that we've been talking about kind of all semester. And these ideas were actually first kind of put together by this guy, James Clerk Maxwell. And he had his paper. Well, he'd been writing other stuff and putting stuff together, but his main paper, 1865, and that had numerous equations in it and numerous observations in it that kind of ended up getting put together later and condensed down into four equations. Okay, so out of this paper and put together by other people like Heaviside, Oliver Heaviside, and a few others. These guys, like some of them are in the name, like Faraday, Gauss, Lorentz. All of this stuff ended up being put together, and out of it we got four main equations. Okay, and these four equations kind of put together the foundation of the study of electromagnetism. And like I said at the start, we've kind of been talking about these as we've been talking about the various parts of physics too. Okay. So if you remember the very first thing we did in physics 2, was we talked about static charges and the electric field that you could get from that. And that happens to be the first of Maxwell's equations, okay? Or what is now known as Maxwell's equations. Like I said, there used to be more than that, quite a few more, but then Heaviside worked on it and summarized them. Okay, so Gauss's law is the first of Maxwell's equations, and the conceptual understanding of this was a relationship between a static E field, so a static electric field, and their source charges. We talked a little bit about this, where if you have a charge but you don't know what the electric field coming from it is, you can put a surface around it and find the flux or amount of E field going through that, and then that tells you something about what the source charge is. And that's kind of what Gauss's law was. Okay, so we did talk a little bit about this when we were doing static E field and stuff like that. The next part we talked a bit about was when we talked about magnetism. So the next part of Maxwell's equations happens to do with magnetism. So this is another version of Gauss's law. So this is another version of Gauss's law, but this one is for magnetism. Okay. And it does this, basically the same thing, works the same way, but it's altered due to the fact that you can't have monopoles. Okay? You can't have monopoles with magnetism, meaning you can't have a single north pole or a single south pole. Whenever you have something with a magnetic field, it's got both. And so with charges, it wasn't like that, right? You could have a negative charge by itself. You could have a positive charge by itself. So there needed to be a Gauss's law for magnetism, but that took into account dipoles. Okay, and Gauss worked on that as well. The third one we talked about recently was induction, and that's the third of Maxwell's equation. Okay, so this is Faraday's law of induction. And what this is how an EMF, or electromotive force, okay, similar to a voltage, can be induced on a conductive loop when the magnetic flux through the surface varies with time. Okay? So what this is basically saying was that if you have a time-varying field or a changing field, you can induce an EMF. Maxwell himself added something to this, so this was later modified by him. And it was modified to state that a time-varying field always accompanies a time-varying B field. I should say a time-varying E field. Okay? Always accompanies a time-varying B field. So now we're learning, oh look, if there's an E field out there, there's got to be a B field as well. And then the last one has to do with currents. And we didn't really talk about Ampere's law too much. It's a similar concept to Gauss's law for static charges, but it's for current. So it's how an electric current, so this is talking about moving charges, can also produce a B field. And Maxwell also added to this, whoops, Maxwell addition for this was that was the fact that a changing E field known as displacement current could also produce a B field. Okay. So this is a different type of current that we don't really talk about too much. But Maxwell's addition does cover that. That type of current is kind of like a current that doesn't exist but mathematically does. It's a little confusing. But Maxwell added that that could also produce a B field. So what was the point of all this? Well, the main thing that you should get out of these equations is that they have the consequence of electromagnetic waves. These are also abbreviated EM waves, is what I'll usually refer to them as. So EM waves, their definition is where a changing B field induces a changing E field, which induces another changing B field, and so on and so forth. Okay? So you get a changing B field or E field, which again then induces the other field. And this can propagate outward depending on the type of wave it is. For EM waves, they propagate, we'll see, at the speed of light when we talk about that. But first, before we talk about more about E and M waves, let's talk about just a brief overview of waves. So a lot of this stuff comes from Physics 1 and mechanical waves, but they're very similar. They have similar definitions, things like that. And so it's good for us to do an overview of them before we talk about E and M waves just a bit more. So what is a wave? Okay. Well, a wave that I shamelessly stole from Wikipedia here is a disturbance of a field, which can also be thought of as like a medium, like air, a drum, pretty much anything. A disturbance of a field or medium in which a physical attribute oscillates. I'll talk about what a physical attribute is. Repeatedly, so this physical attribute oscillates repeatedly at each point, or propagates from each point to neighboring points, or seem to move through space. So let's talk about this one more time. So it's a disturbance of a field or a medium. So like I said, that could be the air. In the case of sound waves, that could be a drum causing a vibration. That could be an EM wave we'll talk about. And what's happening is you have a physical attribute that's oscillating. So the air, it's a gas molecule. Okay, it's oscillating back and forth. And when it does that, it causes the point next to it to oscillate back and forth. So what you're getting, it's kind of like this little picture. You can just imagine, so picture is you get this particle that's moving back and forth, which causes this guy to move back and forth, causes this guy to move back and forth, and this guy to move back and forth. Okay, so A causes B to move, B causes C to move, etc. And so it's moving back and forth and transferring that motion to the particle next to it. So from each point to neighboring points, okay, and it seems to propagate outward, okay, from that original oscillation. So that's what a wave is, okay. Now let's talk about, there are two types of waves that we will discuss. There's a couple more, One's a combination of these two, and then there's another one that's a little bit different. But there's two in this class that we will discuss. Okay. So the first one is a mechanical wave. Okay. And so a mechanical wave is what we would study in Physics 1. It is a local deformation in some physical, oops, I cannot, in some physical medium that propagates from particle to particle, creating local stresses that cause strain in neighboring particles too. And then that again causes more propagation. Okay, so it's like a chain reaction. And the best example of this maybe is like a sound wave. Okay, and this is, you know, variations. Oops. Variations in local pressure that your ears pick up on, and then they vibrate due to the variations in local pressure. This that propagates by collisions between gas molecules. Okay. The main thing here with a mechanical wave, it needs a medium. It needs air to go through. It needs a material to go through. It can't go through a vacuum. Okay? Number two, though, the second type of wave, that's an EM wave. And these are waves that travel through various media or vacuums, okay? So they can travel through both. And these guys are variations, not in local pressure, but in the E and B fields that propagate according to Maxwell's equations. Okay? So they're variations not in local pressure like sound waves, or variations in like the drum, okay, if it's like a drum, but it's variations in E and B fields that propagate according to Maxwell's equations. So again, main distinction. There's others like the speed at which they propagate, but the main distinction is that mechanical waves need a medium to travel through. Okay. Okay. So, still talking about regular waves, we need to now define the parts of a wave. So let's look at the anatomy of a wave. for this guy, here would be the amplitude of the wave, okay, that I'm plotting here, and this would be the x, so this is the distance, okay. Typically a wave, you know, it looks something like a sine wave, right? Oh, let me see if I can... Actually, I was going to draw it with a different color. Okay. And then there's a few, actually I'm going to leave that as that. There's a few things we need to mark here. And I'll define all of this stuff. Okay, we can do that. Okay. Okay, let's define what all this is now. So this is like a typical like sine wave. Goes up and down, it goes positive and, you know, negative below zero, right? And there's a few things that we need to talk about with the anatomy of a wave. Some different terms that you'll constantly hear regardless of the wave that you're talking about. So the first definition actually isn't displayed here. It's the frequency of a wave. And this is the number of cycles that pass by a point per unit time. Okay? It has the equation this, where this is period. Okay, I'll talk about what the period is. So what's a cycle? A cycle is one, or the part of a waveform that doesn't repeat. So it's the part that doesn't repeat. So this goes up, comes down, then it starts to go up again, and then it repeats. So this first part is cycle 1, the second one is cycle 2. So the wave above has 2 cycles. So if you look at this, if I create like a line in space, like right here or something, like I just draw like this, how many cycles are going past this point in time if the wave is moving to the right, okay? That's the frequency. Next up, we have period. That the frequency is defined in terms of. And so this is the, oops, the duration of time that passes as a wave moves past point, or as a cycle of a, that passes as a cycle of a wave, moves past a point. Okay, so how much time does it take for one cycle to move past this point? Okay, that's a period. The next one is wavelength, and this is actually pictured. Okay, the wavelength has the symbol this lambda, so this is called lambda. Oh, and I forgot to mention units of frequency, sorry, are inverse seconds or hertz. I don't know why. And period has units of seconds, right? Because it's a unit of time. Okay, so wavelength, the symbol lambda, as you can see up here, it's the length between any repeating part of the wave. So the length or displacement between any two repeating parts of a wave. Okay, we're almost done. Amplitude is another one, and you can see right here, I kind of labeled it. It's the peak from 0 to the peak. Okay. But what the amplitude represents is kind of like the size of the wave. It is the maximum extent of a vibration or oscillation measured from the position of equilibrium, which would be the 0, i.e. the most, actually I'm going to leave it like this. So it's just the maximum extent of a vibration or oscillation measured from the position of equilibrium. So for example, it's this right here. So as the wave stretches up and down, that's it. Okay, it's the maximum that it can stretch beyond equilibrium. Okay, so the maximum a particle vibrating can move. Okay, a couple things. Energy, I just want to talk about real quick. Waves can carry energy, and there's a relationship between energy, frequency, wavelength, and amplitude, and speed of a wave. Okay, so the speed of the wave is just the propagation of it. Should have probably defined it here. So this is what I wrote up here, v. So speed of a wave, which is rate of propagation, okay, of the wave. So there's relationships between all of them. So let's talk about them. And remember that energy a wave can, the amount energy right here, its definition, remember, is the amount of work something can do. So the amount of force that it can give something. Okay, so waves can carry energy and do force and all of that. So here's some relationships for you. Frequency equals the speed of a wave over the wavelength, and V equals wavelength times frequency if you just rearrange it, okay? But more than that, energy is proportional to the frequency. So as energy goes up, frequency goes up, and inversely proportional to wavelength. Okay? Whoops, forgot to write inversely proportional to wavelength. So that means as energy goes up, frequency goes up, wavelength goes down. But more than that, we'll also see how intensity plays into it. We'll talk a little bit about that. And amplitude squared, okay? And I'll talk about these two and this guy a little bit more soon. Okay? Or later on. We'll discuss later on in this lecture. Okay? So energy proportional to frequency, inversely proportional to wavelength. That's the most important part. But you can also have the intensity, which I'll talk about what that is, power per time per area, and then you have the amplitude squared here, that it's also proportional to. So if you have a higher amplitude, a higher oscillation, the more energy you're going to transfer, which makes sense. Okay. So, let's keep going. We're still not done talking about waves. So we've talked about mechanical waves and E&M waves. They can both propagate in two different ways. So, and mechanical waves in two that we will discuss. There's more than two, but we'll only talk about two. Here, let's in two different ways. But these are the main waves. Okay. Number one, transverse waves. Now, a transverse wave is the type of example that I already gave you. But this is where the particles move perpendicularly relative to the motion of the wave. Okay, that is really, really bad. I'm not good at handwriting. Okay. They move perpendicularly relative to the motion of the wave. So, i.e., rock falling in water. Okay, when a rock falls in water, what do you get? So the rock is like here, here's the water. You start getting these waves that propagate outward, right? That if you look, you know, like you're in a pond, they circle out like that, right? And the motion of the wave is outward. So this is V. So the particles are moving up and down. Okay? But the motion of the wave is to the left, right? It's outward. It's perpendicular. Okay, to that, to making a 90-degree angle. So perpendicular to the motion of the particles. Okay. I should say the speed of the wave, but motion of the wave, right? It's moving, it's propagating outward. And that is perpendicular. Okay. The second type of wave, so the first type, the second type of a wave is a longitudinal wave. Okay. And this is the motion. So if the other one was perpendicular, you can imagine this one would be parallel. So the motion of the wave is parallel to the oscillating particles. Okay? So it moves with the oscillation of the particles. So a really good example of this one would be a slinky. Okay, you've got a slinky. And if you press, so you have a slinky on the floor and you just kind of push through it, what you'll get is kind of like, you'll have periods of compression and expansion. Compression and expansion. So you'll get compression. Ugh, that is bad. Okay. So you'll get compression and expansion as the wave moves to the right. And of course, if you were to plot this wave right here, it would look, you know, it would be this. Okay. So that's kind of how that goes. So far we've discussed a few things. Oops. Okay, so let's just recap everything we've done so far. I talked about how Maxwell's kind of discovery of everything we've been talking about this semester and a couple other things led to the conclusion that E field has to induce a B field and so on and so forth. That's an E&M wave. A changing field induces another changing one. And then we talked about what a wave is, okay, how it's formed. We talked about the two types of waves, mechanical and E&M, and we talked about their anatomy of a regular wave, or any wave really, works for both. And then we talked about how they can propagate through space. Transversely, particles move up and down, or longitudinal, they move parallel. Okay, so now what we're going to talk about is back to energy, okay? So, how much energy does a wave transfer? Okay. We talked about it a little bit. Well, the amount of energy transferred is proportional to the intensity of the wave. Okay? Now, what is intensity? Intensity is defined as the power of a wave per unit area. Okay, well, what is power? Power, if you remember, we talked about it a little bit when we were doing circuits and in Physics 1. Power is defined as the energy transferred per time. Thus, intensity is proportional to the wave, hold on. Oh no. Okay. That was my practice lecture. Okay. Thus, intensity is energy per area over some time. Okay? So it's the amount of energy transfer per area per time. Intensity is also a function of amplitude squared. Okay, so wave amplitude squared. As mentioned before. So if you want the energy transferred by a wave, it is proportional to the amplitude squared, and you can also find it through the intensity, which is energy per area over time. Okay, where it's proportional to that. Lastly, and we'll talk about energy as it explicitly relates to E&M waves in a little bit. So how much energy will be shown later in this lecture. Okay. So how waves carry energy, that's another difference between them. Mechanical waves, obviously, that's dependent on the type of wave, you know, what it's transferring through, or the material it's moving through. And so E&M waves and mechanical waves will carry different amounts of energy. most of the time. So how much energy what we care about, E&M waves will transfer. I'll show that in a bit. But lastly, and this applies to both waves, so both mechanical and E&M, energy and intensity drop off as 1 over r squared. Okay, so it's an inverse square law. 1 over the distance squared. So i.e. inverse square law. Okay. At least for 2D. In 3D, I believe that works a little bit differently. Okay, so now back to E&M waves explicitly. You know everything you need to know to talk about this. So how do you make an E&M wave? Okay. So the creation of an E&M wave needs a varying E or B field. Okay. As I said before, you need a varying field to pull it off. But how people do it, how people create them in the first place, the easiest way is to use an alternating current. Now, we didn't really do AC too much when we were doing circuits. We mostly talked about DC, but you do need an AC current to actually, because it's moving, right? It's moving back and forth. You're using a positive voltage, negative voltage, positive voltage, negative voltage, and flushing those charges back and forth. But you do need one of those to make this happen. So by varying the voltage, we can create a varying E field. Which creates a varying B field, etc. Okay? Alright. That's kind of what the other one was on. I'm just gonna see if I can just recopy this. So this is how an E field, so we already did the anatomy, or the anatomy of a regular wave. So let's look how an EM wave looks. So I'm going to shamelessly borrow from my previous work here. So it kind of looks like this. I guess I can just delete that. Okay, so what we've actually got here is you've got a time varying, or a varying field per space, okay, where the electric field is different at different points in the Y space, or I believe Y space and then Z space out here, or actually in conventional, this is Z space and then this would be Y, but it doesn't matter. And notice they're perpendicular. I'm going to add one more thing on this. V. Okay, so it's moving this way. And this will equal c, which is the speed of light, and I'll talk about that. But this one's in this dimension, this one, the B field is pointing outward in the other. So let me draw this. So this is typically Y, this is typically X, this is typically Z. And so B is in the Y direction, X is in the to the left and right, and then up is Z. And notice E and B are perpendicular, as are E, B, and V. Okay, so they're perpendicular to each other, and they're perpendicular to the propagation of the wave. They are transverse. Thus, EM waves are transverse waves. Okay. Now, as I mentioned before, oops, the rate of propagation of EM waves was derived to be so how fast they move. V equals the speed of light equals the magnitude of the electric field over the magnitude of the B field. And if you actually find these and divide them, you end up getting what we find to be the speed of light. Okay. And so EM waves propagate at the speed of light. In a vacuum. Okay. So let's define the speed of light then in a different way than you're normally seeing. You can use this equation. And if you remember, this was electric permittivity, how an electric field moves through some material or whatever. And this is the magnetic permittivity, okay, for magnetism. Okay, epsilon naught, mu naught. And so C is a function of these guys. And since the reason I said in a vacuum right here, because it can change in other materials. And it can change in other materials because epsilon naught and mu naught will change, which will change the electric field or the B field in that material. Okay? So it's less than C in other media. Okay? C is typically 3 times 10 to the 8 meters per second in a vacuum. And like I said before, V will vary in other media, okay? Because C varies in other media. EM waves have the same relationships as other waves, so they have the same equations. It's just C equals lambda F now instead of V. Or here, as other waves, but the rate of propagation, V is replaced by C. Okay, so C equals lambda F. We can get from this, okay, we can get our electromagnetic spectrum. So from this, and you may have seen the EM spectrum, okay, and this is organized by wavelength, okay. Don't know why that's there. So this is wavelength increases this way, whereas frequency will increase in the opposite direction because they're opposite, inverse of each other, okay? So the wavelength, right, is the length between the different points. So here to here, okay, is the wavelength of that wave, and it's measured in meter. It's a length, okay? Whereas when you start to get smaller and smaller on these, the wavelength decreases and the waves compress together, meaning the frequency of the wave goes up because the number of cycles, because your wavelength is smaller, increase. And of course, energy increases with that as well. Okay, so from left to right here, as the wavelength decreases, you have radio, then microwave, then infrared, which is on the tinge of what we can see. Then we have the visible spectrum, which goes from red to purple. Then we have UV, X-ray, and gamma ray is the most energetic, highest frequency wave in our spectrum. Okay, this is continuous. It's not discrete. That means there's an infinite amount in between here if you measure small enough. Okay. So now, what we need to talk about is energy transfer. Okay. So how much energy how much do they transfer? That's a function of the E field and B field that constitute or create the wave in the first place. That makes sense. So E fields can store 1/2 epsilon E squared energy. B fields can store 1/2 B squared over mu naught, okay? So the total energy stored is added. Okay, so the total energy stored is added together. And can be written in different ways. Okay, 3 different ways to write the total energy storage. If you want it in terms of E field only, it's epsilon naught E squared. If you want it in terms of B field only, it's B squared. Okay. And if you want it in terms of, oh, sorry, get rid of that. I was like, why is it the same? And if you want it in terms of both, you can write it like this. And all of these energies have units of joules per meter cubed. Okay, so that's how much these waves can store. But how much the waves can store isn't the amount they transfer. So it isn't the amount that as mentioned before, is the intensity of the wave. Okay. So here we can write that in 3 different ways again. So the amount of energy EM waves can store isn't the amount transferred. That's their storage capacity. The amount that's transferred is the intensity. And 3 different ways to write intensity. So epsilon naught C E squared. You can write it in terms of B field only. And you can write it in terms of both. But since these depend on changing quantities, right? If you remember back to the graphic of what composes an EM wave, the electric field and the magnetic field are constantly changing as it propagates throughout space. So since these depend on those changing quantities, it would be rather tedious to get the amount of energy transferred over time. So, it's often easier to use the average intensity, okay, to figure out the energy transfer. So I average can be written in 3 other ways, okay. 1/2 epsilon naught C E naught squared, and I'll say what these are in a sec. Okay. E naught are the maximum amplitudes of their respective waves. Okay. Okay. So that's how much energy is transferred. Now, since waves transfer energy, they should also be able to exert forces on other objects, and they do. Okay, so waves can interact with you and exert forces in the process. But in everyday life, EM waves don't affect us much, okay, as far as forces. Okay. They're insignificant, okay? They're very, very small. The amount of force that it can exert on you is really, really small, even compared to something like gravity, which is already pretty small. It only has any effect on us at all because the Earth is massive. That said, though, some technology can or does use this fact. Okay. There's something called solar sails. I don't know if you guys have heard of them. Solar sails, for example, use radiation pressure. And if you remember, pressure is force per area. Okay, so it's the amount of force applied over some area. To travel the universe. Okay. Theoretically, at least. I actually don't know what type of. I really don't know too much about solar sails. I know that you have a sail. It's got stuff on it. It's basically absorbed this energy and accept the pressure, and it's slowly pushed and accelerated away from the source, which in this case would be the sun. And so it can accelerate from any, it's not much of an acceleration, but over a long distance starts to accelerate more and more. So it's really useful in that regard because it doesn't use fuel. So anyway, we're not going to be doing too much with radiation pressure, but I did want to mention it. So to sum it up, in this lecture you learned about, EM waves, and they're a fact from the fact that they basically stem from the fact that electricity and magnetism, we've been talking about this for some time, are inextricably linked, okay? And so they cause waves, okay? They cause EM waves to happen. And we talked about the various properties of waves. We talked about their anatomy, amplitude, frequency, wavelength. Know those terms. Know energy of a wave. Know that waves can carry energy. We talked about the types of ways that waves can propagate. Transverse, longitudinal. And we talked about, so summary. Let's do it this way, so summary. Are inextricably linked. Could be spelled wrong. And result in E&M waves. Okay. All waves share similar traits in definition, like wavelength, amplitude, energy, frequency, the speed, etc. Okay, so you can talk about them in the same way. Mech waves need a medium to travel through. EM waves don't. Waves propagate in a few ways. We talked about just two, which is transverse and longitudinal. So waves propagate in a few ways, and we talked about two of them. We talked about transverse and longitudinal. EM waves are transverse. EM waves propagate at C in a vacuum. We talked about how all waves transfer energy, and we looked at how much energy EM waves transfer. So that's been this lecture on E&M waves. I hope you guys learned something, and I'll see you in the next one.